Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 34, part A, and we're going to introduce bivariate discrete distributions. So last time we learned how to read a z-table, and the reason to do that is if we have this distribution, x is distributed as a normal with mean mu and variance sigma squared, I can transform that to a standard normal using the equation for z, which is the number of standard deviations above or below the mean for x, and solve the problem using a z-table. We also learned that if z is a standard normal distribution, then z squared has a chi-squared distribution with degrees of freedom of 1. So in this section, we're going to look at the joint PMF and the marginal PMF of two variables that are put together at the same time. We're going to look at the mean and the variance. We're going to learn about the trinomial distribution, the multinomial distribution briefly, and go over some properties of the CDF for a bivariate PMF. All right, the CDF of bivariate random variable, or bivariate random variables, distributions. Okay, so before we've been looking at univariate. So we had one variable, and we talked about f of x, and for the PMF, that would be the probability that x is equal to little x. And so it's a probability, and when we solve this, we could say that that's equal to y, couldn't we? So even though we didn't deal with y, we were dealing with x, univariate, the result you could plot as a y if you wanted to. Okay, now we want to deal with two variables at once. And so this is an example where we want to predict the college GPA in the first year, we're going to call that Z, using the high school GPA, X, and the SAT scores, Y. And so we could say that Z is approximately, or is, some function V of X and Y. Okay? So this function is, in our case, we're going to look not just at a function, but at a distribution function. So it's going to be a PMF, a bivariate PMF, and probability mass function. So let's look at an example, and this is one of the easiest ways to understand the bivariate PMF, the joint distribution of x and y. So we're going to toss a coin 3 times. X is going to be the number of heads in the 3 tosses. Y is the number of heads in only the first 2 tosses. If I want to know how many objects or items or outcomes are in my sample space, I take the number of possible outcomes in each trial, which is 2, heads or tails, and raise to the power of how many trials we repeat, which is 3, and that gives me that there are 8. So I could use a tree diagram, and I may have at one point to do this, but I've written out our sample space here as triplets, and what I want to do is I want to find f of x, y, which is this portion, the inside portion of this table. That's what it is, okay? So what I've done is something that's planning ahead. I've put this in order by x. X, why x and not y? I could have done y, but x is easier because it deals with all 3 tosses and y only deals with 2 of them. So in this special case, definitely better to do it by x. So here's x2, x equals 1, x equals 0. Now my strategy here to fill in this table is to, since I've got it ordered by x, I'm going to do this by x. So I'm going to look at x equals 0, and I'm going to see how many outcomes, and there's 8 total, how many of those outcomes correspond to y equals 0, 1, or 2. So here we have x equals 0. And so I look at the first 2, and none of those are heads, so y is equal to 0. And I only have one of these, and so I have x equals 0, y equals 0, that is here. And I don't have any more for x equals 1, so those are zeros. It can't happen in this case. And if I'm just looking at x equals 0, the probability that x equals 0 is 1 divided by 8, that's here. And this is going to be my marginal, what I call the marginal distribution of x okay, in the margin of the table. Now, I go to x equals 1, and here I have y equals 1. Here I have y equals 1. Here I have y equals 0. And so two of these, under x, two of these are for y equals 1, and one of them is for y equals 0, and there are no y equals 2, so that would be 0. And there's 3 of these, so for x equals 1, 3 out of 8. And so look what's happening. I can add up these values across the values of y. I can add these up to get my marginal, and I add these up to get this marginal. And I do that with 2 and with 3, and you get the same result. And then likewise, if I were to arrange this by y, which I'm not going to, but if I did, then to find the marginal of y, f of y, I would look at y equals 0, and I add across all the possible values of x for y, and then 2 and 4 and 2. And those had better add up to 1, and they do. And then the marginal for x, those had all better add up to 1, and they do. And let's also look at the joint, which is the interior here. If I add all of these up, this is f of x, y, the sum of those across x and y, those had better add up to 1, and they do. I've got 1, 2, 4, 6, 7, 8. So 8 out of 8 is 1. So here is how we write the joint PMF of x and y, and then the marginal distribution or PMF of x is written, this is supposed to be a capital X down here, and this is a little x here. And so I sum across the y values of the joint PMF. So the sum of the joint PMF across the y for a fixed value of x, just like we did here. I fix x is equal to 0. I add across y equals 0, 1, 2. I get this. And so this is the probability that x is equal to little x. And the same thing for the similar thing for the marginal distribution or PMF of y. F of y is the sum across x of the joint PMF, and that's probability that y is equal to little y. Let's look at the joint distribution for x equals 2, y equals 1. So we come up here and we look down, x equals 2, and we want y equals 1, and so it's 2/8. And then I want the marginal of x at the marginal distribution of x at x equals 2, and that's going to be, here's 2, so that's going to be 3/8. And then I want the marginal of y at 1. 1 is here, and so that's going to be 4/8. So I've given the definition of the joint PMF already, but what I will talk about are these properties, and I did talk about this a little bit, that since PMF is also a probability, the joint PMF of x and y has to be between 0 and 1, and the sum of all x and y combinations of the PMF, of the joint PMF, has to equal 1. And then finally, if I have some subset A in the sample space, and the probability that x and y are in A is the sum of those x and y's that are in A of the joint PMF here. And then we've talked about the marginal distributions. I want to talk about the independence of x and y. So the random variables x and y are independent if and only if the probability of x equals x and, this is an and, y equals y, that's what the comma means, is and y equals little y is the probability of x, that x equals x times the probability of y equals y, and these are the marginals, right? So we can write this another way, that f of xy is equal to f of x times f of y. Otherwise, they are said to be dependent, not independent, but dependent. So let's look at an example where we roll a fair die twice. We're going to let x be the sum of the values of the two rolls, and y is the difference of those two values, absolute values, so it's always a positive. We want to find the sample space, the joint distribution of x and y, the marginal distributions, and then we'll look at whether they're independent or not. So here's the sample space that I've written out from 1, 1 all the way up to 6, 6 for these two fair die. And remember that the diagonals here have the same sum, okay? And the sum is x. And the difference, that can be all over the place, so we're going to do this by x. That's going to be our strategy of getting our table here, is I'm going to start with x equals 2, and that's here. And we're looking at for y, it's the difference between these two numbers, and that's 0 for this one, and there's only one of them out of 36. So that's also my marginal value, because all the rest have to be 0. There's only one of them. Those two numbers are the same, 1 and 1, so the difference between 1 and 1 is 0. Now, I could go to 2, but I'm going to go ahead and jump to 7. Whoops. I'm going to jump to 7 here. And here's 7. And so I look here, and I've got 1 and 6. That's 5 apart. And this is 6 and 1. That's 5 apart. And so 5 is over here. Oops. So we have here, and that's 5. And then I look at 2 and 5. Those are 3 apart. And so here we have 3. And then I look at 3 and 4, and those are 1 apart. And so that's here. And then the rest have to be 0. And so we do that for every value of x, and that's what I've done here in the table. Now, again, the joint PMF is going to be f of x and y. That's everything inside the table. And if I add up all those values, they add up to 1. Okay? And then marginal of x is here, and the marginal of y is here. So make sure you understand that. And I've come up with some equations, but don't worry about this. I won't ask you to do that. That's not the point of this course. That might be a graduate level course, but not this one. Or just a more senior level course or something. So we want to ask, are x and y independent? And here, what we didn't say, but that you need to get from this is for any xy combination. Has to be true for any or all, I should say, xy combos. So if I find one where it's not true. So I'm going to use 0, 0 here. And so I have f of x at 0 and f of y at 0. So here's f of x at 0, 136, which I put in here. Here's f of y at 0, which is 636. I multiply, I get 6 over 36 squared. And then I look at f of 0, 0. That's 1 over 36. And these are not equal, so x is dependent on y, or x and y are dependent, or x and y are not independent. Okay. And here is another example, and we have f of xy is equal to this quantity, and we want to find the marginal distributions and check that they're PMFs. So I've added across here, I sum across the y's to get the marginal of x, and that turns out to be here, 3 over 4 to the x. And then I do the same thing for the y's. I sum across the x's, and you can walk through what I've done there, and we get our marginal of y. And then we check it. Make sure you check it and you understand this check. And then we want to see if they're independent, so we take f of x times f of y. Here they are. And sure enough, we get f of xy, so they are independent. And I want to point out that the space of this is a rectangle. It goes on infinitely. That's what the dots here are for. It goes on infinitely, but it is a rectangular space. I also want to point out that I could take this and I could say 9, 4x plus y. I can break this up into 4x, 4y. And I can choose any combination. I can make 9 over 4x times 1 over 4y. And sure enough, that is equal to this. This is a function of x only. This is a function of y only. They're not the PMFs. the marginal PMFs, but they're two functions, one of x, one of y. I multiply them together, I get the joint PMF, and I have a rectangular space, and we know that these are independent. So let's look at some remarks, and you can work this one on your own. Next time we'll look at the remarks to see about the independence. Okay, so look at this. We went from example 2, our x and y independent. I chose f of 1, 2. This is example 2. I'll scroll up quickly. Example 2. So 1, 2. Here's 1. Here's 2. That was 0. 1/8. No, not that one. 1. Yeah, 3/8. And 2 is 2/8. So let's come back down here and see what we did. So we have f of 1, f of x 1, f of y at 2. 3/8, 2/8 is 6/64, but f of 1, 2 was 0. They are dependent. Don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. Update any of these documents you need to. And if you have questions, come to virtual office hours. If you can't do that, email me, but email me a picture of your problem and your work. That way I can help you by email. Stay safe, take care, and we will see you next time.